All right, here we go, the granddaddy of them all. Let's do a full-blown truss solve. So I've got my ruler here, I've got my calculator all set and ready to go. I've got my beautiful force template, or excuse me, truss template, and we're all set. So let's take a look at the truss that we're going to solve. So it looks relatively simple. We've got a nice little triangle. We're given our dimensions. We have a force going on there. We've got a pin and a roller. So let's get into it. Step number one is let's redraw this bad boy, replacing our reaction forces, or excuse me, our pins and our rollers with the reaction forces. And I did not draw this to scale very well. Oh well. We'll get over it. Let's get rid of that stuff. Yeah, there we go. So we've got a roller over on the far right side. So we have a perpendicular force going on. So let's go, what? A, B, C. So let's call this reaction force at joint C in the Y direction. I'm going to replace my pin over there in a similar manner. So that is R-A-Y. And we've got R-A-X. And then we've got a force coming from B at 400. Since we're in inches, I'm assuming that we're going to be hanging out in pounds. Okay. So let's, I'm going to modify those to make sure that those puppies are in feet for us. So I'm going to go 30 divided by 12. So we have 2.5 feet. And 40 divided by 12 is 3. Just so we don't have to round quite yet, 3 1/3 feet. All right, sweet. Everything is set up. Now let's figure out if we can even solve this thing. So I'm going to use my static determinancy equation. So I'm going to say 2 times my number of joints, 1, 2, 3, is equal to my number of members, 1, 2, 3, plus my reaction forces, 1, 2, 3. And indeed, 6 equals 6. So we are good to go. Whew! All right, let's get into it. I'm excited about this one. Let's solve for our external forces. Now we've got a decision to make. Are we going into moments first? Are we doing Y first? Are we doing X first? And in my head, in the Y direction, I don't know Ray. I don't know RCY. I'm going to avoid Y because we don't know diddly squat about that. In the X direction, we know one of them and we don't know the other, so that's a good route to go. And if we were to do moments, I'd probably make my fulcrum at A, which means I have one known moment and one unknown. So it's kind of a toss-up between X and moments. Doesn't really matter which one we go first. I'm going to go with our X just to gain a little bit of momentum. So RAX I drew in the positive X direction. So I'm going to keep that guy as positive. Minus the force at B, because that's going to the left in the X direction, which is negative. And then let's plop our numbers in. So we have RAX. I'm going to skip a step, and I'm going to add that 400 to the other side, which means that RAX is 400 pounds. And we probably could have seen that anyway, but we want to make sure that our directions are good. Sweet. Okay. I still don't know any other of my Y forces, so let's jump to our moments. And I'm going to pick joint A just to eliminate those two moments because my distance from the fulcrum for Rax and Ray would both be 0, so those kind of go away. So this is my fulcrum. Let's look at moment B. I'm going to kind of record that over here. And let's see, if this were my fulcrum and I were to push it this way, that's going to give me a, what, counterclockwise moment, which we defined as positive. RCY, if I push up, is also going to be counterclockwise, which is also positive. Now my gut tells me that RCY is actually going to be going the other way, but let's see if the math adds up. So MB is force times distance. So we have 400 pounds times my distance. So let's figure it out. That perpendicular distance from my fulcrum to my line is going to be 2.5 feet. Not 3 1/3, 2.5. And then RCY, or excuse me, MCY, my fault, is going to be my reaction force times its perpendicular distance. So if we kind of follow that line up, we have a distance of 3 1/3 feet from my fulcrum. Equals 0. Sweet. Okay. So I'm going to multiply 400 and 2.5, and I'm going to subtract it from both sides. So 400 times 2.5 is 1,000. So I'm going to subtract 1,000 from both sides. So we have RCY times 3 1/3 equals negative 1,000. And our last step would be to divide by 3 1/3. Divided by which is going to be about 300. Excuse me, negative 300 pounds. So again, that negative is telling me that I need to flip that guy. So let's do it. Let's flip it. Instead of going up, that must mean that RCY is going down to make sure that our moments are nice and even. Sweet. So then the last thing we need to do is get into the y direction. So we've got ray from what we drew is positive, so I'm going to keep that as positive ray, minus RCY, because we just found out that RCY is going downwards in the y direction, equals 0. So we've got ray minus 300 equals 0. So in order to maintain static equilibrium, ray has to be 300 pounds. So maybe I'll update it up here as well. Fantastic. Hey, not too shabby. So we've solved for all of our external forces. Let's start our preparation for the internal forces. So I'm going to use SOHCAHTOA. Let's try to find, let's go for angle C over there. We already know angle A is 90 degrees. Let's find this guy. So we've got 2.5 feet. We got 3 1/3 feet going on there. So we have my opposite side, we have my adjacent side, which means we're going to be using tangent. Oops, I should probably move this up so you can see what I'm actually doing. Sorry about that. So I just kind of set up that triangle. I identified the length of each of those sides, and I'm just starting to do trig to figure out what that angle is going to be. So since we're dealing with opposite and adjacent, we're dealing with tangent, theta, is equal to my opposite, which is 2.5, divided by 3 1/3. And if I want to get that angle by itself, I have to use inverse tangent. So tangent inverse 2.5 over 3 1/3. And if I type that in my calculator, remember, in my TI-84, I'm going to go second tangent, 2.5 divided by, let's go 3 1/3. So I have an angle of 36.87 degrees. Fantastic. So then our last step on this first page is to redraw and prepare for our method of joints. So we've got our schmancy triangle going on. We know ray. We know Ricky. We know Rax. 400. We know FB And we know our angle right here, which is 36.87. We've got A, we have B, and we have C. So in order to prepare for our internal forces, I'm going to erase the middle of all of our members so that we're assuming that all of our forces are in tension, which means they are stretching out the joints. Fantastic. So now let's move on to our internal forces to figure out how much force each member is providing. Great, so I am going to switch out my sheets, and for the sake of the video, I am going to cut out the last thing that we just solved for. And I usually don't do this, but just kind of nice so I don't have to bounce between the two for the video. So give me a hot sec to do that. All right, here we go. Next step is we need to figure out the internal forces of my truss, and I need to figure out which truss do I want to start off with. Okay, so I'm going to look at like the most knowns or the least unknowns, probably the least amount of trig. Really, all of these are pretty good picks. So I'm not super worried about that. I think I'm going to start with A just because everything is perfectly straight up and down or left and right. So that'll make our job pretty easy starting off. So let's pick joint A. And I'm going to put this force diagram, and I'm going to isolate it in our spot right there. So we have Ray going up equals 300 pounds. Also going up, it looks like we have the force from A to B, so I'm going to say fab. I also have racks at 400 pounds. And I have the force from A to C for right now going to the right. Now, as I look at this, clearly it is not super balanced, and you can probably tell right off the bat what the values are going to be. You can tell what direction they need to be. I'm going to work through the calculation just to make sure that everything is good, because if I screw up this portion of the truss, it messes the whole thing up, and that is never a good feeling. So let's start with the X direction shenanigans. So we have racks, which is positive because it's going to the right. We have FAC, which is also positive because that is going to the right, since we're assuming that everything is in tension. So we have 400 pounds plus FAC equals 0. So if I subtract 400 from both sides, my FAC is negative 400 pounds. And remember, if we come up with that negative value, what that means is that force is actually in compression, and we need to flip that thing. So I'm going to take FAC, we can write 400 if we want to, and we need to flip that arrow because in order to maintain that static equilibrium, it's got to be going back the other way. And I think we'll find a similar thing with our Y direction, but let's set it up anyway. We have FAB going up, so I'm going to leave that as a positive value, plus Ray going up, which we know has to go up based on our external force calculations, equals 0. And if we start plugging numbers in, FAB plus 300 equals 0. So FAB equals negative 300 pounds. And again, we come up with that negative number, which has to mean that member is in compression. So just like before, we gotta flip it. So I'm gonna flip it right now. FAB going like that. 300 pounds. Sweet. Okay. Not too bad. Let's go to our next little chunk. And we already kind of know, or it looks like both these are going to be pretty gosh darn similar. Since I already solved for that angle, let's go to joint C. Now I could easily do my 90 minus 36.87 to figure out what angle B is, but we already did the work. We're good to go. And I'm going to transpose that guy over here. So we've got RCY equals 300, and we know it's going down because of our external forces calculation. We've got FCB, which we're going to have to break down into FCBX and FCBY. And we also have FCA, which is something we actually solved for. And remember that we found FAC to be in compression, which means that it is pushing on that joint. So FAC we know to be 400 pounds, but it is in compression, so it's pushing on that spot. So it looks like we just need to solve for FCB, and we are good to go. And it looks like I could choose X, I could choose Y. It doesn't matter. We have one known and one unknown for both of those. Let's do, I don't know. I feel better about RCY. Let's make sure that everything is square for our Y direction stuff. So RCY is going down. I'm going to write that as a negative value. So negative RCY. The way that we drew FCB, the sense is left and up, which means that FCBY is positive, at least the way we drew it. So let's start breaking that down. Negative 300 pounds. And we need to break this down in terms of trig. So FCB is my hypotenuse. If I'm looking for that opposite side, I must be using sine of, what was our angle? 36.87 equals 0. Sweet. So I'm going to go FCB. I'm going to add 300 to both sides. Sine 36.87. I should probably work out the whole thing, shouldn't I? So then our FCB equals 300 divided by sine 36.87. Let me do that real quick on my fancy schmancy calculator. 499.9988. Okay, 500 pounds. And that number came out to be positive, which means that puppy is in tension. Cool. Dang, we solved for everything in that force diagram. If I look at what we've got up here, we solved for FCB. Earlier we solved for AB. Hey, we got everything, so we don't even need this last guy. Perfect. So then our very last step is we're going to record our final answer. So one last time, we're going to record our truss like this. Oh no, I did it again. My dimensions are all off. Let's get rid of that thing. Okay, so we know RCY is 300 pounds. We know, what's our other reaction force? Ray equals 300 pounds. We were given FB, which was 400 pounds. We solved for Rax, which was 400 pounds. So now let's dig into our other little members there. So FCB, the thing we just solved for, is 500, and that's in tension. So I'm going to record that on the member. FAC, we calculated to be 400 pounds in compression. And then last but not least, I'm going to rotate this thing. FAB, we found to be 300 pounds, and that was also in compression. Beautiful. So there we go. We've got our fully solved out truss. We didn't even need that last little bit of our template, but the process remains the same for all of our other trusses.